Hello, everyone. How are you?
Hello. The test was nice.
It was nice. I hope
Yes.
so. I hope so. I tried to make it so that it's more or less on the topics we went through and so on. And then on the other hand, it would be difficult enough and not too difficult. I don't know if I managed to do that, but
Yes, I think so.
okay, very good.
But I think it was clear, like you could see which, for each question, you could see exactly which ideas we should use.
Yeah,
Because it's really similar to some of the examples.
yeah, I tried to do that. First thing, I haven't managed to go through your papers yet, but so I'll be doing it later. I guess today I'll try to do it. Also, I have many things still to do today, but I'll try to go through your papers. But then we are ready to go to solve this together here. I don't know if we should wait a little bit more so that every one of you is here present, or we'll start. What do you think?
It's 3:02 right now. Maybe I will send them a message and then
Yeah,
maybe
please,
we can start when they join.
please.
Maybe some of them can't join this session.
Mhm.
So maybe some of them cannot join.
Okay.
Maybe they are busy or something.
But good news, I am recording it, so if anyone cannot attend right now, then it will be recorded. The session will be recorded. All right, then I guess we'll start.
Actually, Sadiq said he will join.
Oh, very good.
Wants you to wait. He says his laptop is.
Okay.
Slow.
We'll wait a little bit then. Meanwhile, I can draw here on the screen already problem number 1. So, yeah, let us see if Sadek is here. Not yet. So we have basically here 2 options of solving it. One is using centripetal acceleration and the other taking derivatives of coordinates. Is that right?
What?
The derivatives of coordinates. We can say that, if here this guy here has coordinates x and y, then okay, if this here is angle alpha, let us say, then we have coordinates here of this one, and we can calculate that one, and then we can take the derivative of the these x and y coordinates, for instance. This is one possibility of doing it. The other is centripetal acceleration. Yeah?
Teacher,
Yes,
what's the direction of the speed here?
direction of speed is
Perpendicular.
yeah.
Well, just a moment.
It
must be perpendicular to the first rod.
Yeah, it is. Yeah, but it starts rotating. So in the process, I just a little bit curved so that it will start rotating because speed is kept constant. So it starts rotating. Now, let us do first using centripetal acceleration. So if this moves that way, No, and now angle alpha is here. I guess this is angle alpha. No, it's the other way around. Not this one. OPA is alpha. Sorry, OPA. This here is alpha. And so we have here acceleration centripetal because there is speed is constant, so there is no tangential acceleration for this point A. No, P, which I can, let me check the letters. Yeah, P, point P. For point P, we have only centripetal acceleration and no tangential acceleration. So acceleration of this point P is v squared divided by L. And it is on the angle alpha with respect to the between these two bars, which means it is alpha over 2 is angle here. So that if we project now the acceleration of point P to the vertical axis, then we see that AX equals v squared divided by L multiplied by sinus alpha over 2. Okay?
Yes.
And then this here moves just, it is 1, this is 1, this is 1. So 4 times more. So here
on the vertical only.
Prime is 4 times AX. Do you agree? Project.
Why is it prime?
I'm just denoting A.
Okay.
This. So this was A, this is A prime. A prime we need to find. Okay, this is 4 times AX, which is 4v squared divided by L and sine of alpha 2.
I think we can do the same thing for a y prime.
Yeah, and we can do actually exactly the same thing with y. Now, as for
But
A,
it is 2 times,
y,
not
exactly, we have b squared divided by L and cosine of alpha over 2, and AY prime is 2 times AY. And so this equals, because of that, v squared divided by 2v squared divided by L and cosine alpha over 2. So that.
I have a question.
Yes?
In my solution, I left it as AX and AY.
Oh,
is that fine?
That's fine, yeah. Okay. Because you have the full expression. On the other hand, you can add them too, in which case you say you obtain that A prime by modulus is 2v squared divided by L, and then go square root of cosine square alpha over 2 plus 4 sinus square alpha over 2. And you can simply rewrite it if you like. I'm not saying simplify, probably it's a little bit simpler, as 1 plus 3 sinus square alpha over 2.
Could you rotate the laptop, please?
Sorry?
Could you rotate the laptop, please?
Yeah.
Yes, that's.
And for the velocities, it's exactly the same.
Yeah. Velocity with velocity is exactly the same way. Yeah. Acceleration was a little bit more difficult, right? But velocity is easier. So
I think.
Yeah.
If you find the velocity, actually, ux is going to equal to 2 times the. If you differentiate the speed, it is going to directly give you the acceleration.
I think just what we need to do is we need to substitute v square L for with v, and then sine with cosine and cosine with sine. Is that right?
Yes, I think so.
Yeah. So I can immediately write for v as v prime equals v square root of 2v square root of sinus square alpha over 2 plus 4 times cosine square alpha over 2. And if we like, we can take it like 1 plus 3 cosine square alpha over 2. Okay,
Teacher, in the second equation, what is written? From up. The second one.
This.
Up.
This. Two-
AX, I think.
2v
The
alpha plus 4 cosine
no, not
squared.
this. In the acceleration
AX
tool.
equals,
Sorry?
AX equals V squared over sine alpha over 2.
Because we have, if we have ax like that, we have vx equals to v multiplied by cosine alpha over 2. And here we have y is v times sinus alpha over 2. We can see that if here is v square, here is v, and here is sinus alpha, here is cosine alpha over 2. And here is the same thing. Yeah, I guess, yeah, here is 2.
Here, where is the H direction you take?
Sorry?
Where is H direction?
Right now, x is horizontal and y is vertical. I think. Or is it it's the other way around? It's the other way around, I guess. Because I took ax as sinus alpha, it's the other way around. X is vertical and y is horizontal.
Okay, now.
All right. So first problem done.
Done.
Yes.
So probably it's enough. We shall not do it using coordinates because this is, I think, better method of doing it. Now, problem number 2. And problem number 2. 2 balls are thrown simultaneously. One is straight up and the other not really straight up. And then we want to know when if first ball has PV, then what is the minimal speed u, so that these two would collide in here. And the distance is L. Okay, this is here is L. And now, as you probably made a good guess, that we need to consider this in a free fall frame. If it's free fall frame, then the balls move, free falling frame balls move along straight line. So we need to have this ball just move in the direction of the second ball. So if this had got V, so it means that that U must have vertical component exactly the same as this V, but it must should have also certain horizontal component. So Ux. Okay, so in order for this to meet with that, this velocity minus that velocity must be horizontal. To that end, a vertical component of this velocity here must be the same as here. Now, and they need to have, it needs to have enough, big enough horizontal component that there is, it will manage to collide with this before it falls below the ground, before it returns back to ground. And now, now we just need to compare the time during which it is in the air. So T equal GT square over 2. You better do that way. That velocity v goes to minus v. You have v goes to minus v, vertical projection. But this minus v is v minus gt. So t equals 2v divided by g. Does it travel
I have a question.
Yes.
Are they thrown at the same time?
Sorry?
The two balls are thrown at the same time,
Yes.
right?
Yes.
Oh, I see.
It is clear that due to energy conservation, once it is back here at the ground level, velocity has turned to minus v. And then because that minus
Yes.
v minus gt, so we obtain it immediately t equals 2v divided by g. Of course, there are many other ways of obtaining it, but I think this is the easiest way.
It seems so obvious now. I am ashamed I did not solve this. No, not completely, at least.
Okay.
Teacher, now what are you going to do?
Okay, now,
Why you calculate this time?
sorry?
Why you calculate the time for
Because I know that this ball here needs to have vertical component V and some UX. If UX is too small, then it will not have, it would require more time to reach the other ball than the time it spends in the air. So UX needs to be enough to reach the other ball over this time here. So we need, we have conditions that UX times T is equal to L. So this is a shortest possible T, smallest possible UX. It needs to reach over time T, which is the time during which the first ball is in the air. It needs to reach during that time the other ball. So a speed, horizontal speed multiplied by time must be equal to that, the distance. And so, from here we obtain UX times 2V divided by G equals to L, from where minimal value for UX is going to be LG divided by 2V. And so the minimal speed is going to be now U minimal is square root of X component plus Y component 4V squared divided by G squared plus L squared G squared divided by 4V squared. Okay?
Why is that? What is the vertical component in this case? Should just be V squared, right?
Sorry, sorry. My mistake.
Yes, okay.
My mistake. Yeah, first is just V squared. Sorry. I just.
Also, I have a question.
Yes.
Could we have used the maximal trajectory? So what I did in my solution is that I used the what is it called? The maximum graph. I forgot what it's called. But
the envelope of trajectory.
The envelope, yes, the envelope. I used the envelope.
Well, the thing is that actually here it is not necessarily optimal. This point does not need to lie on the envelope because this is a little bit different problem. It is not reaching this with minimal speed, but reaching this within a given time frame. It needs to reach this point.
Okay, I see.
Over a fixed time. Mm-hmm.
Okay, I see.
Yeah, you need to be careful and just if you have some result, it is applicable only if all the conditions are met. Here, the condition is not met that the envelope is valid when you have no time limit, but here you have time limit during which it needs to reach. Okay?
Okay, yeah.
Teacher, could you explain the time again?
Okay, so we consider things in free falling time frame, free falling reference frame, and then there particles move with straight line. And so we see that this ball here must move directly towards that. Now, relative velocity is a difference of those two velocities. Because of that, it is clear that this ball here must have the same vertical component as that, so that in the difference remains only horizontal component. So it must, the velocity must be vertical v plus certain ux. And so now the requirement is that the ball, now this velocity here with arbitrary ux will guarantee that these two balls would meet if they were not to reach ground. But if we had unlimited time. But now our time is limited because it is required that that ball to collide with that before the ball to ground. And so we need to now take this into account. The time for this ball to reach ground is here.
So they will collide.
Yeah, and they need to
immediately.
And they need to collide sooner than that. Oh well, this is the longest time which is allowed. So
clear.
At least during that time. And so on the other hand, we want to keep this speed as small as possible. So if it's as small as possible, the travel time from here to here is as long as we can afford, and as long as afford is given by this. So because of that, we require that this ball reaches that ball over this time here. So that relative velocity ux times travel time t is equal to the distance L.
Okay, clear.
Next one.
Okay, next one. Yes. And next one is rhombus. And here we have a ball. And then we have 2 alpha here. And now, we need to consider equilibrium. And perhaps the most difficult task actually here to figure out is equilibrium for this rod here, or this rod here. Well, first thing is that here, because this here is hinged, so it can freely rotate here, and because of that, tension T here is along the rod. You only can stretch the rod and not bind. So you can stretch it only, and here as well, only stretch.
Okay.
Yeah. Now, but with this rod here, it's a little bit different. That we have here 3 forces applied, one here, and one here. Okay, here you can say that why it is along the rod, because this hinge here does not create torque, but only force, and then we have torque, force applied here and force applied here, and this rod here must stay at balance, so sum of torques must be 0. Now, if you consider torque acting on this rod here relative to this point here, then it is obvious that arm only one force T is applied, arm must be 0. So this force torque here T must be applied along the rod. Okay? Because otherwise, if it were not applied along the rod, then we would have torque here, which is not good. So because of that, tension force here in this rod must be along the rod. But for this rod, this is not the case, because here we have 3 forces, one here, and one here. So, here we know the direction, because Newton's third law, force here is the same direction of that T. This is interaction force of this rod and that rod. For this force, we know the direction which acts on this rod here. Now, for this, we also know, because this is normal force, and this goes to the center of the ball. Here is normal force which acts on the rod. But now, what might be the most difficult is where is directed force which acts on this rod from the side of that rod?
I think if we take the torque at this point, we can find the torque at the point at the bottom, and then it doesn't matter where the force from the other rod is pointing.
That's not quite enough, because we need to relate now angle, and if we do that, actually we do need the direction here of this force here. But can you figure out what is the direction of the force which acts on this rod from the side of that rod?
Should be horizontal to the left.
Yes, very good. It is horizontal because of symmetry. So because of symmetry, it cannot be on this arbitrary angle, because figure is symmetric, but then this figure would be not. So one acts that way, one rod pulls the other that way and the other that way. The figure is not symmetric. The only symmetric figure is when these both two are horizontal. Okay?
Okay.
Can you see that? So due to symmetry, it's clear that force exerted on that rod from that rod must be horizontal. Okay, this is T1, this is T2. Okay?
Okay.
And now the rest is easy. The rest is easy. Now we write down the torque balance on this rod here. And what we know is that we make, of course, now extend, as we did during lectures, intersection point T1, T2. Now, torque of T1 and T2 is 0, which means that the normal force N must also have 0 torque with respect to that point, which means that it must go through this point here. So actually, we need to perhaps correct a little bit the figure. So here is the ball. Ball goes here. Okay, so that the normal force here goes through that here. And now we can extend this. So here we have right angle. And then we need to solve some trigonometry. So here this is radius r. Now let us see this side here. Okay, if this is 2 alpha, do you agree that this is alpha over 2, this angle here?
I'm not sure, so can we
Okay,
derive it?
all right, let us see. This plus that. Okay, this here is alpha over 2, this angle here.
It's just alpha, not
Alpha.
alpha over 2.
This, yeah, sorry, yeah, so of course, because it's 2 alpha, yeah, my mistake.
Okay.
Yeah, my mistake, it is alpha, yeah. So yeah, this is also alpha, yeah. So this is alpha, because this is obviously alpha.
Okay.
Then we have here a right triangle and similar right triangle. And so this must be also alpha. Okay?
Okay.
Okay, and the rest is geometry. So do
Yeah.
we do it?
This side here is L. Okay, so
So is this one on the right.
yeah, but this side here, from here to here, it is now here we have 2 alpha, so we can write as L
2L sine alpha.
yeah 2L and
Sine alpha.
minus alpha. Right? Okay, I draw height here, and then this here is L times sinus alpha, so from here to here is 2L sinus alpha. Okay.
Okay.
And then this side here, because of that, is now 2L sinus alpha and multiplied by, once again, sinus alpha, so sinus square alpha.
Yes.
Okay, and if so, then radius
Or-
R, which is in this triangle here, so R equals now 2L sinus square alpha multiplied by tangent alpha. Okay, and that is the answer.
I have a question.
Yes?
What is the theorem for sine 2 alpha?
Ah,
Because my solution has that. Okay.
here you are. 2 sine alpha cosine alpha.
Yes, so I think I got the same solution, just in a different form.
Very good. Okay. Clear to everyone? Everyone happy?
Everyone happy.
Shall we take next problem?
Mr. Calda,
Yes.
so the final answer was 2L sine cubed over cosine.
Yeah, the final answer was 2 sinus square alpha tangent alpha, which you can also write as 2 sinus cubed alpha divided by cosine alpha. Yeah, L also, of course, L.
Okay.
And you can also write, if you like, this as yeah, if you take sine alpha cosine alpha, then you can take it as cos sinus 2 alpha and divide it sinus square alpha, tangent square alpha, something like that.
Yes, tangent squared.
Okay, if you like.
Next one.
Next one. Next one, we have cone.
Teacher, before the next one.
Sorry?
Can it be solved problem 3 by potential energy?
Well, if in principle, yes, I think if you write express, but it is going to be a long way. So you assume that the radius is r, and then you express the height of the center of mass, and then take derivative, find the lowest position of the center of mass by maximizing over angle alpha, and then you can find the relationship between angle alpha and the radius of the ball. In principle, if you can do that math, then yes.
Okay.
Now we have here at the surface of a cone, we have a ball launched on the inside surface of the cone. And well, as we discussed, conical surface can be expanded into unrolled, so to say. And on unrolled surface, we see that the body must move along straight line because there is only normal force, no forces which would cause it going to side.
Yes.
And so just what remains to do is to draw here like unrolled version of it. So first we need to find what is the okay, it particle starts here and it has done 10 degrees here. 10 degrees here. Okay. And
can you change the pen?
sorry?
Can you change the pen
Yeah.
to black or?
Let me see. I have different pens here. Okay, red is quite good right now.
Yes.
So now first I need to figure out what is the angle here. Gamma. If we unroll it. So if we unroll it, suppose this here is r, then this here is so from the side view of the cone, this is r. So height here h is r multiplied by sinus alpha, cosine alpha. Height is r times cosine
Beta.
No, we need actually this side here. We don't know cosine. We need to sine alpha. So here, this radius r is r multiplied by sinus alpha.
Sine beta.
Yeah, okay, beta. Sorry. So this is beta. And then this parameter here is 2 pi r sinus beta. So that this angle gamma is going to be in radians. Would be if we divide 2 pi r sinus beta, we divide by r. So it is 2 pi and sinus beta in radians. Now, shall we calculate in degrees how much it is?
62.5.
How many degrees?
62.5.
62.5 degrees. Very good. And then we have here on the 10 degrees is going. Now what happens? It goes here and then reaches this point here. Now what happens next?
It will be like it disappears from this right side and appears on the left.
Yes.
So what you can do is mirror the figure.
Yeah, so this is 65 degrees. 60. What is 62.5?
62.5.
Okay. Yeah, so it basically continues. And we need to just make another 62.5 here, like that.
I think we should redraw the figure to be more accurate.
Okay, 62.5. So let us
That way we can get the answer
It
immediately.
is 62. It is slightly less than 60. If we had 60, then we would have here 3 times we have
180.
yeah, 120, but now it's a little bit more, something like that.
But it's close enough, I think.
Yeah,
Even
it's
if it was
good enough,
60.
yeah. Okay, and so it goes like that, and blah, 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 blah. Now it is clear that it passes 1 time and 2 times. So two full rounds.
Yes.
Okay, so n equals 2. As for minimal distance, we take here perpendicular. And
We have L.
this is a minimal distance, and this is a travel distance to minimal distance. So if this here is L, and this is 10 degrees, so this length here, travel time to the closest approach is L multiplied by cosine of 10 degrees.
Which is like 0.98.
0.98 L. And so travel time is that 0.98 L divided by V. And that is the answer to the first question.
Yes.
Okay, here you go.
Clear.
P5.
Problem 5, yes, now. And now we have this thing here. Okay, and now we have a mass here M, and here we have M naught here. And here is also M. And now the total weight is 2M plus M naught multiplied by G. So this weight is balanced by 2 normal forces. So this is going with 2N. So that N is M plus M naught divided by 2 times G. Now, because this is actually edge of slipping, because we make these two as far as possible from each other, so it means that this is in the verge of slipping, then friction force here is mu times N, which is the horizontal component of T, Tx, okay, equals Tx, and this equals to now mu multiplied by M plus M naught divided by 2 times G. Okay?
Yes.
Now, what about Ty? Ty,
1
Yeah.
over 2 M naught G.
yeah, Ty, obviously, because 2 times Ty balances weight of the rope. Ty is M naught G divided by 2. So that now tangent alpha equals to Ty divided by Tx equals
M naught G.
M naught
Just
G.
M naught without the G.
Yeah,
Because it will
M
cancel.
G cancels away. M naught divided by mu and 2M plus M naught.
Yes.
And if we write like, we can also write cotangent. It looks probably better because this is going to be mu and 1 plus 2M divided by M naught. And that's the answer.
Very good. Lagrangian.
Yeah, now Lagrangian. Everyone happy?
Yes.
Everyone happy.
Now Lagrange.
Session was 2 hours. Now only 1 hour.
Okay, if we have some remaining time, we can either you can ask me questions or we can, we are free to do whatever we want to, with that remaining hours. Just the discussion of problems is going better than the worst case scenario. So,
Worst case scenario when no one solves anything.
yes.
We have a lot of questions.
Yes, exactly. So now I have one the generous coordinate is x here. So b here disappears and goes to here. So the mass which goes over here is total mass multiplied by x divided by pi and
Sure, the pen, please.
IR.
sorry, yeah.
The pen, change. No, we cannot see.
Oh, sorry.
Yeah. The blue pen is bad.
Black.
Okay.
Try black. There is black.
Okay, let me see. I have two blacks. Which one is better? I have actually, if I open my bag, there are still some more. There are still some more whiteboard markers. Maybe some of these are even better. I have also green. Green is, I think, quite okay. But let me see. Oh, this black is good. Now, yeah, okay. So mass here is mass of the water multiplied by x divided by pi and r, which goes away. So that now we have and the other parameter is how much the center of mass moves. Let this be y. Of course, you feel free to use whichever other coordinates, but well, this is one option. And then we have now vertical kinetic energy and horizontal potential, horizontal kinetic energy. So we have here now. Well, how I did myself when I tried to how this problem works out, it was so that I consider. I calculate kinetic energy as a kinetic energy in the center of mass frame and add the kinetic energy of the center of mass. Well, what is easy actually is the kinetic energy of the wheel. Kinetic energy of the wheel is just because of rolling and because of y, and this is going to be m and y dot squared, because moment of inertia is mr squared. So if you calculate, you obtain it like my dot square is the kinetic energy of the wheel.
I have a question.
Yes.
Shouldn't there also be a term for the water?
Yeah, I think I am going to write it.
translated?
Yeah, I am going
Okay.
to write it. This includes only wheel.
Okay, okay.
Yeah. Okay, because water starts also with W. Let me put it ring instead. Kinetic energy of ring, and then we have kinetic energy of water. And now, as of water, I myself was doing it that way. I consider first kinetic energy in co-moving frame with the ring. With the ring, if water just rotates. So this is going to be now. Well, actually, what we need to have is the kinetic energy in the center of mass frame, because theorem states that kinetic energy is kinetic energy in the center of mass frame and kinetic energy of the center of mass. So kinetic energy of the of the kinetic energy of the center of mass, and this is kinetic energy of the system in the center of mass frame, and that's what the theorem states. Now, what would be very convenient for us to calculate is kinetic energy of the water in the frame where the center of ring is at rest. But then again, the difference between those two is very small. The center of mass frame and the frame where the center is moved. So center of mass is somewhere here, but it has certain horizontal component, center of mass of water. It has certain horizontal component, but then it has also certain vertical component. Now, a center of mass of the water in horizontal components, this is what we are going to calculate. But as for vertical speed, then vertical speed is basically.
I have a question.
Yes.
For the kinetic energy of the water, can we assume that it's going to be translating with the wheel horizontally, and then just say that it's going to have rotational velocity that's like, how can I say this? Yeah, x dot, basically.
Yeah. Maybe say this better, actually, guys, because things seems to be a little bit complicated for calculating the kinetic energy of water. Let us just going to integrate. It is not too difficult to integrate. Do you agree?
Yes, I was about.
I think.
What do you mean?
I think in this case, the easiest bet is to just integrate. The integral is not going to be too difficult. So, we're going to divide kinetic energy of the water by integration, and then we have in the frame where we consider the in the frame where the wheel is at rest. So there they have water moves in this direction in y dot as y dot. So if we take here now angle alpha here, let us take angle alpha so that alpha is with vertical. Then we integrate with from minus pi over 2 to plus pi over 2. So this angle here be alpha. Here this is alpha. Okay. Then water moves in that direction with y dot. And so that vertical speed v vertical is y dot times sine of alpha. Okay.
Isn't it x dot?
Yeah, x dot. Sorry, thanks. Yeah, x dot. X dot and x dot. I made confusion now between these two. Yeah, x dot times sine of alpha, and the horizontal is going to be now is going to be y dot is the speed of the frame, and we need to add up this x dot times cosine alpha. This is going to horizontal speed. Okay. So that the speed squared is going to be v squared is going to be x dot squared. Sine square plus cosine square gives 1. Then there is plus y dot squared, and then there is a cross term plus 2y dot x dot cosine alpha. This is going to be velocity squared. And now we need to integrate.
Can't we use superposition?
Yeah, this basically is superposition, addition of velocity. So you add the velocity of the frame, which is y dot, to the velocity of the water parcel here, which is x dot in tangent direction. And in tangent direction, it has got speed x dot, and so vertical speed is x dot sine of alpha, and horizontal is x times cosine x dot cosine alpha. It's just a superposition, adding of velocity.
Okay.
and then Kw equals, now let me take right here. Let me write here. So so Kw equals integral of mass density, which is dm. Okay, let me write it now. X dot square plus y dot square plus 2y dot x dot cosine alpha, and multiplied by dm. But dm is total mass divided by pi and multiplied by angle d alpha. M d alpha divided by pi is dm. Okay? And integral goes from minus pi over 2 to plus pi over 2. And then this thing here equals to m over pi. Now here we get pi x dot square pi plus y dot square pi, and here plus 2y dot x dot. Cosine integral is sinus from minus pi half to plus pi half gives us plus 2. Okay.
Mr. Calder.
Yes.
In the case of the water, why can't we do the same thing that we do for the wheel? Like,
Sorry?
in the case of the water, why can't we do the same thing that we did for the wheel? Like add translation kinetic energy plus rotational kinetic energy.
I was the reason was that in principle you can do it, but what is a little bit troublesome is that we need to have kinetic energy in the frame of the center of mass, and so we need to figure out first how the center of mass moves, because center of mass moves. Water level changes, center of mass moves from the center. It was at the center, it is no longer at the center. So just in principle, we could do that, but finding the kinetic energy in the center of mass is not really necessary easy task. So it seems to me that it is easier now to find it by integration in lab frame. And so this all thing together, we can write it like some pi's cancel away. M x dot square plus y dot square plus, and here goes 4 divided by pi, and x dot y dot. Okay, and this is kinetic energy of the water, and so now we just need to have we need to write down the Lagrangian. Now I think I don't need this figure. I can make a space so we can continue here a little bit to the right, writing Lagrangian. Lagrangian is, maybe I switch to red. Red I think was quite okay. Lagrangian equals kinetic energy total. We have still here my dot square. And here we have another my dot square. And so this goes to now m x dot square plus 2y dot square. This plus that. And then plus 4 divided by pi x dot y dot. And then we have minus potential. Now minus potential is here the water goes from raises by x, so it is going to be minus, potential is growing, so it is minus, mass is mx divided by pi r times g and another x, so it goes to x goes to square. Okay, and this is the Lagrangian. Okay, mass goes before the brace. We can mass this just keep like that. And now we don't have any dependence on
Teacher,
y. Yes.
the factor of y dot squared is 2. Did you add also the translation or just the rotation?
Yeah. So y dot was here, but y dot is also here.
This is the whole,
That's why it goes.
or just rotation.
This was a whole system. Yeah. Wheel, bus, plus water.
Okay.
And so now d over d. First, let us write what is constant, because this does not depend on y. So dl over dy dot is constant. dl over dy dot is going to be 4y dot plus 4 divided by pi and x dot. And this is constant, and we can put the constant equal to 0, so that we have 4 cancels away. So x dot is pi y, x dot equals minus pi and y dot.
Teacher, could you repeat the potential energy?
Potential energy is so that, okay, the water level goes up here down by x and here up by x. So it's as if water here is moved to here. So the height difference is x. So we have mass, which is mx divided by pi r, and we multiply this by g and height, which is x. So this multiplied by x and g. All right. MGH. M is this one here.
I have a question.
H is x and g.
Okay.
Okay.
Tricky question.
Yeah.
I think.
All right. So like that. And then we have the other equation, dl over d dx dot. Now d over dt of dl over dx over x dot over dx dot.
I have a question before that. What would happen if we substitute x dot in the Lagrangian as the result that we got? Would it still be correct, and could we still use it?
Just to be sure, don't substitute before. You do derivative and then substitute, because that's how it is supposed to work.
Okay.
And so we take x dot, which is now m2 x dot plus 4 over pi y dot equals to minus, and now derivative here, 2x divided by pi and r and g. And now we can substitute this thing over here into here. So we have now d over dt. I think mass is also here, but mass is cancelled away. Now, if we put x dot as y dot as x dot divided by pi, y dot as x dot divided by pi, this goes to pi square.
Teacher, why is it just y dot, not y double dot?
Right now, I still don't have y double dot. We have everywhere y dot.
The upper equation.
There will going to be, because I have time derivative here. But right now, I have no double dots yet.
The upper equation.
Sorry?
When you take the partial derivative for y dot, because we do not have y, so this will be 12.
You mean
The
this
time
here?
No, the first equation, the first one
This,
after, yes, this
this.
is equal to constant or equal 0?
I put it equal to 0 because I can consider frame wide is 0. It is constant, but I put the constant equal to 0.
Okay.
Is dl over dy dot, what is here? It is 0 because Lagrangian doesn't depend on y. This term here is dl over dy dot. This term here is dl, this term of d over y dot. All right, shall we continue? We plug in here y dot as minus x dot divided by pi. So this is going to be now 2 minus 4 divided by pi square and x dot.
Yeah, we can just make it x double dot and remove the derivative.
Equal minus 2xm divided by pi and r and g. So this is going to be 2 cancels away. So x double dot equals to minus m g divided by, no, m goes away, g divided by r. And pi, and here goes 1 minus 2 divided by pi squared to the power of minus 1.
What did you do here?
Sorry?
What did you do here?
I just take derivative x dot goes to x double dot, and I divide left hand side and right hand side by this thing here. That's all.
Okay.
M cancels away. I shouldn't have here m because I divide already by m. And so omega squared equals g divided by r, and then pi. Let us just bring this pi here into the denominator, and pi square minus 2. Okay. All right.
Okay.
So this was like a most time-consuming task of the all, but then again, it is just quite a standard if in terms of Lagrangians. The most troublesome was by expressing kinetic energy of the water. The rest was easy.
Yes.
Okay.
How much would we get if we did not express the energy, the kinetic energy of the water properly?
I subtract some.
Because I think like the Lagrangian part is just math, like the rest is just math.
Yeah. The main thing is because if you had mistake only in expression of Lagrangian, yeah, well, of course this is mistake, and in those kind of things you just need to be careful, and this shows you were not careful enough. But then again, if you grasp the main approach and main steps, what you need to do, and if you did not make any mistake in that, well, you'll get the most part of the points, definitely.
It is not a small mistake, though.
Yeah.
I will see.
Yeah.
When will you correct the solutions?
I'll try. I'll see how long it will going to take me. So I'll work with today, but I have some other things also what I need to do today. So I'll do as much as I can. Hopefully today, but not definite commitment. Not definite commitment, but hopefully today.
Okay, and one last question. What would be a good score on the test? What do you think?
Well, I think the problems as themselves were not very easy. So I think I am quite satisfied with you if you get half of the marks. But of course, anything more than that, I'm really happy.
Okay, that's good to hear.
Yes.
Approximately when will we
Sorry?
receive the marks? When will we receive the marks? Approximately?
I just said that I'll try. I'll do my best to finalize the marks today. But if not, then just I'll let you know. But I'll try to do it tonight.
How will you send them?
Sorry.
How will you send them to us?
How I'll send you the marks?
Yes.
I can send to those few of you of whom I have email addresses. Yeah, you yesterday gave me your email address, but then again, I did not write it down, and later on, I did not get it from Zoom. So if you want, but now you sent me all your solutions. I can send it to every one of you.
Because you sent it to Sadak.
I got your email with the solutions now, so I should make just reply and say.
Oh, yes. Okay.
Yeah.
Okay. Okay, then. I guess I will go.
Okay. Yeah. Just before you go. So how did you feel your training? Was it good?
Yes, I
Course.
think it was very good.
Glad to hear. Glad to hear.
I think it is the best training so far.
Oh, I'm really glad. I'm really glad to hear that. Okay, but then keep up good work. I was also quite happy with you this time because I had very good attendance of you. I kind of felt that you have been doing your job properly and doing studying. Now I'm really eager to see how you managed to do your test. But I have been very happy with you during this training too. Okay, then good luck to everyone, and hopefully we'll see somewhere when the coronavirus has been put under control, then hopefully we can meet.
Hopefully.
Yeah.
Yeah.
Okay, then
Yeah.
all the best to you all.
You too.
Yeah.
Goodbye.
Bye-bye.
Bye.